Good day everyone! So we are here to explain and discuss to you the steps of our chosen asymmetric security algorithm entitled Diffie Hellman key exchange algorithm. Diffie Hellman algorithm, widely known as the key exchange algorithm or key agreement algorithm, developed by Whitefield, Diffie, and Martin Hellman in 1976. That's why it's Diffie Hellman, because they get it from their surnames. So this algorithm, the purpose of this algorithm is to enable two users to securely exchange a key that can be used for subsequent encryption of messages. The algorithm itself is limited only to the exchange of secret values or keys. So, there's user A and user B. User A can be the sender and user B can be the receiver, or both of them are sender and receiver and wants to send messages. But before the exchange of messages, the messages will be encrypted. But before the encrypt of message, both the user A and user B will calculate some values and generate same key. Take note, same key. Okay? So how this algorithm works? For the first step, select Q as the prime number and A as alpha, which is the primitive root of Q. So let's take an example. Here, Q is equals to 11 and A is equals to 5. So let's go to the second step. User A key generation. So let's go first to the user A side or user A key perspective. So what are we going to follow? Select XA. So there must be a value of XA, and the condition here is XA less than Q. As I've said a while ago, that Q is equals to 11. So whatever the value of XA is always less than Q. Now, calculate public YA. In this equation, YA is equals to alpha raised to XA mod Q. So whatever the value of YA will share to the user B. So let's go to the user A key generation example. Here, XA is equals to 3, where the condition is XA less than Q. So XA is equals to 3 less than Q is equals to 11, so 3 less than 11. YA is equals to alpha raised to XA mod Q. A is equals to 5, and then our XA is equals to 3. So 5 raised to 3 mod Q, which is 11. So 5 raised to 3 mod 11 is equals to 4. So our YA, the value of YA is equals to 4. So how do we get that 4? I will explain to you the process of how do we get that answer and how do we get that value of YA, which is 4. So in the equation, 5 raised to 3 mod 11 is equals to 4. 5 raised to 3 is equals to 125. Okay? So 125 divided by 11. So where do we get that 11? 11 is our Q. 125 divided by 11 is equals to 11.36. Then subtract to 11. Where do we get that 11 again? That is from 11.36 answer. So 125 divided by 11 is equals to 11.36 minus 11 is equals to 0.36. Then multiply to 11, which is our Q. So 125 divided by 11 is equals to 11.36 minus 11 is equals to 0.36 times 11 is equals to 4. So that will be the value of the YA. And this is step also in the step 2, as I've said a while ago, that YA shared with the user B.
So step 3, user B key generation, select XB. So there must be a value of XB and the condition is XB less than Q. We all know that value of Q is 11. So whatever the value of XB is always less than Q. Now, calculate public YB. YB is equal to alpha raised to XB mod Q. And then, YB shared with user A. User B key generation example. Here, XB is equals to 5, where the condition is XB less than Q. YB is equals to alpha raised to XA mod Q. A is equal to 5, raised to xb, which is 5 also mod 11, which is r cubed. So, if we calculate, the answer is yb is equal to 1.
And the step 4 is the calculation of secret key by user A. In the equation, k is equal to yb raised to xa mod q. The value of yb is already calculated at step 3, which is the value of yb is 1 raised to xa, which is 3, mod q, which is 11. So, 1 raised to 3 mod 11 is equal to 1. That means k is equals to 1.
My name is Kate Josie Castillo, and I shall be discussing the step 5 of the Diffie Hellman key exchange algorithms. So step 5 is the calculation of secret key by user B. And through this, we have the formula, which is k is equal to ya raised to xb mod q. So by following that formula, we have our example will be leading up to 4 is raised to 5 mod 11, and which means that our k will be equal to 1. So with this, in step 4, we can see that both k's are equal to 1, and any subsequent messages that is encrypted to k will also be 1.